In modern ecosystems, amphibians are defined by their small scale. They are delicate, lightweight, and physiologically confined to the margins of their habitats. This size limit is a byproduct of how they breathe. Most amphibians rely on gas exchange through their skin, which requires a high surface area to volume ratio. As an animal grows, its internal volume increases exponentially faster than its surface area, meaning a giant amphibian would eventually be unable to absorb enough oxygen to support its own mass. Yet, in the Permian period, Prionosuchus plumeri managed to bypass these constraints. Reaching lengths of 30 feet and weights of up to 2 tons, this predator occupied the same ecological niche as a modern crocodile. While the massive temnospondyls of the ancient world are extinct, their ecological role as giant, fully aquatic predators is occupied today by the cryptobranchids. These are the giant salamanders of Japan, China, and North America, living fossils that have remained virtually unchanged for millions of years. Achieving this monstrous size required a complete surrender of the flexibility typically associated with their class. To grow this large, they had to commit to a total, permanent dependency on the water. The first sacrifice was terrestrial mobility. To support a giant body, these amphibians allowed their limbs to degenerate into weak, vestigial steering paddles, effectively trapping them in the aquatic environment. Without the buoyancy of water to counteract gravity, a giant amphibian skeleton is insufficient. On land, the sheer weight of its own body would cause its internal organs to collapse under their own mass. We can see this scale today in the modern Japanese and Chinese species. Reaching weights of over 50 pounds and lengths of 5 feet, they are massive enough to require specialized handling, appearing more like river monsters than modern amphibians. This commitment to the water is absolute. By forfeiting the strength needed to walk on land, they gained the mass required to dominate the riverbed. To solve the oxygen deficit inherent in a 5-foot frame, these creatures evolved specialized anatomy. Their flanks are draped in deep, fleshy folds of skin, which maximize the surface area available for oxygen absorption. This system only functions in lotic environments, ecosystems where the water is freezing cold and fast-flowing. The rapid current washes away oxygen-depleted water from the skin, replacing it with fresh oxygen that diffuses into the capillaries. If the current stops, an oxygen dead zone forms almost immediately. Without the friction of moving water, the giant salamander begins to drown in place. Tethered to these high oxygen currents, they evolved into the ultimate sit-and-wait ambush predators. They detect pressure changes in the current through sensory cells in their skin. When prey drifts close, their jaws snap open with such speed they create a vacuum, sucking the fish whole into their mouths instantly. Even their reproductive strategy is a slave to the current. Male den masters guard their nests for up to 7 months, continuously fanning the eggs with their tails to maintain the constant, highly oxygenated flow their offspring need to survive. Every element of their biology, from their wrinkled skin to the way they raise their young, is powered by the unbroken movement of the river. The fossil record demonstrates the danger of such specialization. 270 million years ago, the tropical lagoons of the Permian began to dry up due to regional climate shifts. Because Prionosuchus had sacrificed its terrestrial mobility for aquatic size, it was physically unable to migrate to new water sources. As the lagoons shrank, the 30-foot giants were trapped, eventually dying out as their environment vanished. It is a lesson in the fragility of giants. Hyperspecialization becomes a lethal trap the moment the ecosystem changes. Today, modern human infrastructure is recreating the conditions of that ancient extinction. Concrete dams and weirs sever migration routes and transform fast-flowing, oxygenated rivers into warm, stagnant reservoirs. Secondary pressures from deforestation and agricultural runoff cause fine silt to wash into the riverbeds. This sediment fills breeding dens and coats the salamander's sensitive skin, physically obstructing their ability to breathe. While habitat loss is a critical threat, the immediate reality for these animals is physiological. Because their biology relies on the friction of moving water, they are literally suffocating inside our stagnant reservoirs. Humanity is now forced to re-engineer the river systems we have broken. This requires intensive manual intervention. Conservationists are now building specialized bypass ramps to allow giant salamanders to scale concrete weirs, while teams of scientists scuba dive into freezing currents to manually relocate North American hellbenders to safer waters. These efforts are temporary lifelines designed to buy time for the protection of intact lotic environments, the rare stretches of river where the water still moves fast enough to support giant life. giant amphibians have survived for 300 million years by outsourcing their basic biological needs to the flow of the river. If we stop that water from moving, we stop the monsters from breathing.